So today we're going to be starting our acids and bases unit. So we're going to look at how to name them. That way whenever you see them, it's just a simple identification thing. These are all just a bunch of arbitrary rules, so you don't have to actually know anything about acids or bases to get them, so it's a good place to start. It should be a little easier. There is definitely going to be a little bit more memorization in this section of the notes and kind of this unit as a whole than there usually is. So for those of you who are good at that, great. If not, make sure that you're staying on top of things, making flashcards, all that good stuff. There are definitely some things in this set of notes that you're going to need flashcards on through the rest of the unit, so I really recommend that you make flashcards or maybe a Quizlet or something like that. And then you can just keep adding to your stack or your deck as you're going through, as you go through the unit, so that by the end, you're solid and good to go. Alrighty, so first off, we're going to start with naming acids. So acids are always going to start with a hydrogen. So that means that in the formula, if you ever see an H at the beginning of it, it is going to be an acid. In this class, you will never see an acid that has that does not have an H at the beginning. There are some that exist, but that's a whole different branch of chemistry that we're not going to worry about. So if it starts with an H, it's an acid. If it does not start with an H, it is not an acid. And that's about all there is to it. With water being sort of the exception, because we'll get to that later. But anyway, so when we go to name acids, if the acid does not have a polyatomic ion in it, the way that we're going to name it is we're going to add the prefix hydro. So remember, prefixes come before at the beginning of the word. And then we're going to replace the ending of that second element with ic acid. So what we're going to do, so like for example here for hydrochloric acid, let's get a color that's not red maybe. So I'm going to go through that process. So since we have Cl there, or chlorine, that is not a polyatomic. So because it's not a polyatomic, I'm going to go ahead and put my prefix hydro. Then I'm going to go ahead and write chlorine. But I'm going to need to chop off the end of it. So we'll replace the end there. And then kind of like back when we were doing ionic stuff, I'm not going to be super concerned if you like chop off too much or too little. Just don't go crazy with it. If you don't hit it exact, it's fine. Not a big deal. I'm looking forward to you understand the gist of what you're supposed to be doing. Alright, so we chop off the ending and replace it with ic acid. So hydrochloric acid then is going to be the name for HCl. And so that's all there is to it. So you're not actually doing anything with the hydrogen here. All that's doing is telling you that you have an acid. So it's kind of showing up back here. And then again, the hydro is just because this was not a polyatomic. If this was a polyatomic, then we'll follow this set of rules. So if there's a polyatomic, if it ends in ate, we're going to change the ending to ic acid. And if it ends in ite, it's going to change to us acid, OUS acid. And then you'll notice there's no hydro here. There is one exception though. So if the acid contains the word sulfur, instead of like sticking with the name of the polyatomic ion and then chopping that off and doing all that, all we're going to do is just simply use the word sulfur, and then we're not chopping off any of the ending, we're just simply adding whatever that was on there. So for this H2SO4 here, we see we've got, like, normally this would be sulfate, and so if we were to go through everything, it would be, we would chop the ending off and make it ic, so it'd be sulfic acid, but for whatever reason, sulfur acids are just really, really old, and so we've just kept the name that it was. So we just simply wrote sulfur because there was a sulfur compound in here. And then since it came from sulfate, we're using the ic acid ending, so sulfuric acid. If this was sulfite, so that would be H2SO3. Since it's ite, we're going to end it in us acid, so that would be sulfurous acid. So just be careful with that. That's the one exception, is that sulfur compounds make things weird, just because old dead white guys who did all the chemistry stuff decided to be arbitrary about it, and now we're stuck. But yeah, so if we go into some more simple stuff, so H2CrO4. And by the way, if you'll notice all of these, they've been crisscrossed. So like we have, some of them have H2s, some of them don't. It's because of those charges. Acids are ionic compounds. So whenever it gets to the point where you have to make the formulas for them, make sure you crisscross every single time. That is very, very important. Okay, so for this one, so this is polyatomic, CrO4. It's definitely not just a single element. So we're not going to put hydro at the beginning. So I'll start with writing this down. So if you look on the back of your periodic table, CrO4 is going to be chromate. And then, of course, we need to chop the ending off. So chop off the 8. And since it ended in 8, I'm going to use ic acid to replace it. And that's it, chromic acid. Easy peasy lemon squeezy. For this one, so I've got NO2, so if we check that out, that is again a polyatomic, so no hydros. And we're going to start with nitrite. And again, we need to chop off the end. And since the ending was ite, we're going to change it to us. So that's going to be nitrous acid. And that is all there is to it. So on your own, go ahead and name these. Go ahead and pause it real quick. That way you can get through them. And then you can hit play and double check to make sure you got them correct. Okay, so let's change the color. Let's go to green. So for HBr, so first off, Br, that's bromine, that is not a polyatomic, so I know that I need to start the name with hydro before I do anything else, because again, that's the standard for if you're just starting with a normal element. Then I've got bromine, but I'm going to chop off the end and replace it with ic acid. So hydrobromic acid. For this one, I've got NO3 attached to the H. NO3 is nitrate. So first of all, that is polyatomic, so I'm not going to use hydro. So I would write nitrate, but I'm going to chop off the ATE. And remember, 8s get replaced with ic acid. ClO2, that's going to be chlorite. And again, this is polyatomic, so no hydro here. So we would start writing chlor, and then I'd have my ITE, but that's going to get chopped off, and ites get replaced with OUS acid. And then down here, so CO3, carbonate. Again, this is polyatomic, no hydro at the beginning. If I could spell, that'd be fantastic. Nope, don't want the highlighter. Alright, so carbonate, chop off the 8, and it gets replaced with ic acid. So again, it's just a matter of memorizing when you use hydro, which is only if it's from the periodic table. If it's from polyatomics, we leave it off. And then if we have a polyatomic, and then also if it's just the element, like HBr here, it's an automatic ic acid on the end. So if it's from the periodic table, start with hydro, end with ic acid. If it's from the polyatomic ion list, remember we'll just write it as is, then chop the ending off and replace it with ic acid if it was an 8, or us acid if it was an ite. And then remember, sulfur's weird. If you have sulfate or sulfite, those are really the only two. Instead of writing the sulfate or sulfite, you're going to write sulfur and then add either the ic acid or us acid, depending on whether you had the 8 or the ite. So, shouldn't be too terribly difficult. So go ahead and work backwards. So based on the name, figure out the formula. And again, remember, acids are ionic, so you are going to have to crisscross every single time. So go ahead and pause, and then hit play when you're done, or if you get stuck. Okay, so for hydroiodic acid. So I see the prefix hydro, so that means that automatically I'm looking at the periodic table. So hydroiodic acid, so that's going to be made up of H, which has a +1 charge. And then the iodic part, so the element that starts with iode or iod is going to be iodine, so that's what it used to be. And iodine is going to have a charge of 1 minus. Because it's in the 7th column, so that means it wants to gain 1 to get to that full octet of 8. If you need a review on that, make sure you go back and look at those notes. Or let me know if you want tutoring videos, whatever. So when we crisscross, that's just simply HI. Acetic acid, so there is no hydro out front, so I know that I'm going to be looking at the polyatomic list. So acetate, and again we'll start with our H+. Acetate is going to be C2H3O2. I'm doing this from memory, so if I mess that up, use whatever is on the polyatomic list, but I'm pretty sure that's what it is. So when we go to crisscross, it's just simply H, C2, H3, O2. I'm going to change the colors because these are running together. Alright, dichromic acid. Again, there's no hydro, so to the polyatomic list, look for dichrome, and then I know it used to be 8 because it's ending in ic acid. Same thing up here, I knew it was acetate because it was an ic. So dichromate, so if we've got H+, dichromate is going to be Cr2, O7 2 negative. So this is where crisscrossing is really going to be important, because now it's not just HCr2O7, because that 2 comes down, H2, Cr2O7. Alright, and then the last one, let's do orange. So sulfurous acid. So remember, with the, since this is a sulfur compound, it's going to be a little bit weird. So I know that it's not from the periodic table, because it is, because it does not start with hydro. So I've got my H+, and then, so sulfurous, so us tells me it was the ite, so that means I'm dealing with sulfite, which is SO3 2 negative, and then we go to crisscross, H2, SO3. So that's all there is to it. So it's just, again, a matter of memorizing those rules. And again, they are arbitrary rules, so you are going to have to just drill them into your head, whether that's through doing the assignments or through, flashcards, whatever it takes. Get it into your head. It's not that many rules, but it can still get a little, well, am I supposed to do this or that? So just make sure you're real solid on it. Okay, so just real quick now, a list of strong versus weak acids. So strong acids are going to dissociate completely. So that means that if I were to put this into water and dissolve it, all of those hydrogen ions and all of those, whatever the other part is, whether it's polyatomic or just something off the periodic table, but all of those are going to completely break apart and they're going to be completely floating on their own. And you do need to have this list memorized. There are only 7 of them, so it shouldn't be too terrible. And then there is also a little bit of a pattern to a few of them. So if you look here, like HCl, HBr, and HI, those are right in a row on the periodic table, like ClBr and then I. So helpful to remember those 3. Then also the ClO4 and ClO3. Those are, again, pretty similar. And then you got your randoms, H2SO4 and HNO3. So just, again, making sure you memorize those. Again, and this would be a great thing to have on a flashcard, just like write strong acids, and then just work through memorizing what each of them are. Then there are weak acids, which do not dissociate completely, and that is literally every other acid that exists ever that we know about. So that means that since they don't dissociate completely, when I dissolve them, some of them are going to break apart, but not all of them. So if I were to, for example, have HF or hydrofluoric acid, and I go to dissolve it, and I were to be able to look with a really strong microscope, I'm going to see some H pluses and some F minuses floating around, because it does dissociate some, but I'm also going to see some HF stuck together, because it's not a complete dissociation. Whereas if I look under a microscope for any of these 7, I'm going to see only H pluses and then whatever that thing is that's attached on there. So if I'm looking at like HClO4 under a microscope, I'm going to see some H pluses floating around. I'm also going to see some ClO4 minuses floating around, but I will never see an HClO4 together. They're all going to be separate with the strong. With the weak, we're going to see a mix of them. So that's the difference between strong and weak acids. So again, a lot of memorization here. Okay, then the last bit, I think, for acid stuff is the number of hydrogens. This is very, very simple. I'm pretty sure there's a multiple choice question on the test that's like, which one of these is monoprotic or diprotic or whatever. Please don't miss it. There's always a few people who miss it every year. This should be very, very simple. Monoprotic means there is one hydrogen. And the reason for that we're using these terms protic, so remember all the hydrogens on these were H+. So since it has that positive charge, that means that it lost an electron. Hydrogen normally has, if I'm going back to proton, neutrons, and electrons. So protons, it's element number 1, so it has one of them. Neutrons, the atomic mass is 1.01, so that means that there's basically 0 neutrons on most of them because all that mass has come from that one proton. And normally, it would have one electron to balance out the proton, but since we've lost an electron, we have none of them. So all of these hydrogen ions are simply just protons floating around. There's no electrons there, there's no neutrons there, they're just simply protons floating around. So all of these terms where it's talking about protic, that's where that's coming from, because it's literally just a proton. But anyway, not super necessary, but just so you know where it's coming from. So monoprotic means there's only one hydrogen in there, so like HCl, there's only one there. Diprotic means there are 2, you got the H2 there. Triprotic means there are 3, we have the 3 there. That's about as hard as it gets. Again, this is just to show you where that protic word's coming from. Okay, so for bases, bases are going to be much easier than acids are. For naming them, both for naming them and for figuring out who's strong and who's weak. So for naming, it's the exact same as any other ionic compound. So there really shouldn't be anything new here. This should just be brushing off cobwebs. And then the vast majority of bases have a hydroxide ion on them. Most of them do. If they don't, I'll give you another, there will be some other way in the problem to figure out whether it's a base or not. And when we get there, I think it's next week, or the next video, we'll talk about that a little more. Alright, so we'll go ahead and name or write the formula for the following bases. Again, go ahead and try to do this on your own, because this is just old stuff. It is purely just ionic naming. So go ahead and give it a pause, and then when you're done, go ahead and pick it back up. Okay, so for the first one, NaOH. So for the first part of this, that's sodium. So this is going to be sodium. The second part is OH, and OH is the polyatomic ion hydroxide. So it just gets sodium hydroxide. Easy peasy, lemon squeezy. Then this one, NH4OH. So NH4, that's the polyatomic ion ammonium. So we got ammonium. And then OH, again, is hydroxide. And that is all there is to it. So again, these are much easier than acids are. Lithium hydroxide. So now I need to do the formula. And remember, these are ionic, so you have to crisscross every single time. So I'm going to go ahead and change the color, because now we're going to start getting some stuff running into each other. So lithium, remember it's going to have a charge of 1 plus. Hydroxide, 1 minus. So these are a nice, simple thing. That's just going to be LiOH, because it's just 1 and 1. Then for magnesium hydroxide, we've got magnesium, which has a charge of 2 plus. OH again has a charge of 1 minus. So when we crisscross, you need to make sure that you're being careful with that. So since there's a 2 goes down here, remember OH is polyatomic. Anytime there's more than one of them, remember you have to put parentheses around it. So Mg, OH2. This is really the only time that you should really ever get hung up on base stuff. It's just simply if you when you're crisscrossing, and then when you're crisscrossing, just to make sure that that you put parentheses around the hydroxide if you need it. So again, literally anything other than one hydroxide needs parentheses. All right, and then we've got strong bases. So strong bases are going to be any metal hydroxide from groups 1 and 2. So remember, those are the alkali or alkaline earth metals. So if we look at the periodic table real quick, so any kind of hydroxide made up of any of these here, so lithium, sodium, potassium, rubidium, cesium, francium, or beryllium, magnesium, calcium, strontium, barium, radium, literally any of these are going, if they're a hydroxide, are going to be a strong base. If it is literally anything other than those, then it's considered a weak base. And just like strong acids and weak bases, it's based on what did they do when they dissolve. So strong bases are going to completely dissociate. So we look under a microscope at, let's say, NaOH, sodium hydroxide. I am only going to see Na pluses and OH minuses floating around. I am never going to see any Na and OH stuck together down there. Same thing with KOH, BaOH2, and again, all of those other metals from groups 1 and 2, or the alkali and earth alkaline metals, they're all going to be completely dissociated if they're with a hydroxide. And then again, literally every other base is going to be considered weak. So we look under a microscope, we're going to see both the OH minus and whatever the other part was, and that whole base together. All right. So, any questions? Let me know. But that should do it.